Lesson 9.1, we will look at how to find factorizations of integers and monomials and find the greatest common factors of integers and monomials. How are prime numbers related to the search for extraterrestrial life? In the search for extraterrestrial life, scientists listen to radio signals coming from faraway galaxies. How can they be sure that a particular radio signal was deliberately sent by intelligent beings instead of coming from some natural phenomenon? What if that signal began with a series of beeps in a pattern comprised of the first 30 prime numbers? Beep, 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 and so on. We're going to go in the Wayback Machine and look at the basic definition of factors. Recall that when two or more numbers are multiplied, each number is a factor of the product. Some numbers, like 18, can be expressed as a product of different pairs of whole numbers. This can be shown geometrically. Consider all the possible rectangles with whole number dimensions that have areas of 18 square units. The number 18 has 6 factors: 1, 2, 3, 6, 9, and 18. Whole numbers greater than 1 can be classified by the number of factors. And I want to make the connection here between the factor t that I like to make and the nice geometric pattern they showed here. We could have 1 times 18, or 2 times 9, 3 times 6. And I like this model to organize factors because the next factor of 18 would be 6. And sure enough, I already have it accounted for. So I know that I have all the factors of 18 there. And geometrically, you can see these are all the rectangles that have an area of 18 that have whole number factors. A whole number greater than 1, whose only factors are 1 in itself, is called a prime number. So the first prime number is 2, then 3, 5, 7, 11, 13, 17, and so on. A whole number greater than 1 that has more than 2 factors is called a composite number. 4 is a composite, it's 2 times 2, 6 is 2 times 3, and so on. 0 and 1 are neither prime nor composite. Okay, this is stuff that you did clear back in elementary school, factor 22, and classified as prime or composite. So I'm going to use that factor t again. I could do 1 times 22. It's even, so I know 2 will work. And guess what? 11 is prime. I am done. We could write that out in ascending order: 1, 2, 11, and 22. Because there is a factor other than 1 in itself, this is a composite number. This is going to be quick. Factor 31. Okay, 31. My factors are 1 and 31. So since the only factors are 31 in itself, it is a prime number. Boop. One of the other skills that you did in previous classes is writing a prime factorization. Corrections may have just said write this as a product of primes, but when a whole number is expressed as a product of factors that are all prime numbers, the expression is called a prime factorization of the number. Now for these, I like that good old factor tree method. We could do 84, well I know 4 will work. 84 divided by 4 would be 21. And then factors of 4 are 2 and 2. Factors of 21 are 3 and 7. So in factored form, I could write that as a prime factorization. 2 times 2 times 3 times 7, or 2 squared times 3 times 7. This is something new to algebra. We can do the same thing with negatives. Well, golly gee, negative 1 times 132 is negative 132. And then guess what? We can do the exact same thing we did before. I'm going to use 6 and 22. Then 6 is 2 times 3, and 22 is 2 times 11. So we could write that as negative 1 times 2 times 2 times 3 times 11, which is a little nicer in exponential form. 2 squared times 3 times 11. Okay, we've already gone over all of the quote-unquote hard stuff from the lesson. What we add next, the algebraic stuff, is actually kind of easier, looking at factored form. A monomial is in factored form when it's expressed as a product of prime numbers and variables with no variable that has an exponent greater than 1. Now, I think it's a little goofy that we can have the number part have exponents but not the variable, but I didn't get to make the rules. They were given to me. Here we go. So the number part we know. We're going to have 2 times 3 times 3, and the variable part is going to be x times x times x, because that's what x cubed means, times y times y times y. And that is a stretched out version of the same thing. Okay, first of all, negative 26, we know we can take out a negative 1, and then 26 is 2 times 13. So we've got negative 1 times 2 times 13 times r times s times t. Beautiful. Not the most exciting thing ever, but not terribly stressful. Okay, next we're going to look at the greatest common factor, which you have also done in previous courses with numbers, and that is the hard part. The greatest common factor, is kind of the words define it. 2 or more numbers may have some common prime factors. Consider the prime factorization for 48 and 60. So you can see they've got 2 2's in common, and they each have a 3 in common. So they circle the common prime factors, and then the product of these prime factors, 2 times 2 times 3 is 12. That's called the greatest, largest, common, the same factor of 48 and 60. The greatest common factor is the greatest number that is a factor of both numbers. Of both means the common part of the greatest common factor. Okay, this restates the same thing. The greatest common factor of 2 or more integers is the product of the prime factors common to the integers. The greatest common factor of 2 or more monomials is the product of their common factors when each monomial is in factored form. If 2 or more integers or monomials have a greatest common factor of 1, then the integers or monomials are said to be relatively prime. Okay, we're going to start off going old school here. This is from the Wayback Machine. 12, we could say is 3 times 4 is 2 times 2. 18, what do we want to do? 9 times 2, 3 times 3. So I'm looking for the commons. They both have a 3, they both have a 2, and that's what's the same in both of them. So my greatest common factor is 2 times 3, which is 6. 27 we could write as 9 times 3. 9 is not prime, so 3 times 3. 15 is just 3 times 5. So our primes that are in common, we have a 3. That's it for the numbers. Okay, the variable part is super easy because we can just look at, if we want to write it in expanded form, we could, well, what they call the factored completely form. Okay, I'd already circled the 3's are in common. Now that I wrote it out in the completely factored form, I can see that there are an A in common and a B in common. So my greatest common factor is going to be 3AB. Now, to me, it is easier just to look here and go, to be the greatest common of the variables, you have to have the smallest exponent. So the smallest exponent for the A's is 1. The smallest exponent for the B's is 1. The smallest exponent for the C's is none because there's no C in that first one. So I only get 3AB. Renee has crocheted 32 squares for an Afghan. Each square is a 1-foot square. She is not sure how to arrange the squares, but she does know it'll be rectangular and have a ribbon trim. What is the maximum amount of ribbon she might need to finish the Afghan? Okay, I'm not sure why you'd have an Afghan that is 32 feet long, but I guess whatever. Okay, so it could be 1 by 32. It could be 2 by 16. 3 doesn't work. It could be 4 by 8. 5 doesn't work. 6 doesn't work, and we already have 8. Okay, so those are dimensions that she could have for her Afghan. I'm still not sure why she'd want it by 32. But for the perimeters then, the first perimeter would be 1 plus 32 is 33, and then we'd have to take that times 2. So she'd have 66. 2 plus 16 is 18 times 2 is 36. 4 plus 8 is 12 times 2 is 24. If I were making an Afghan, I would use that one, but she wants the maximum, so the maximum she could have is 66 feet of ribbon to go around that Afghan. The greatest common factor, which is abbreviated GCF, of two or more monomials is the product of their common prime factors.